Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. Last time I introduced you to the concept of internal energy and the idea that this internal energy can be decomposed into two parts: the kinetic energy, which is an intramolecular energy possessed by individual molecules and closely associated with temperature, and potential energy, which is related to attractive interactions among the molecules. We explored the origins of these interactions and then examined a particular model of a Lennard-Jones fluid to see how these interactions were related in non-ideal behavior in gases, and supercritical behavior, and condensation of a gas into a liquid or solid. My goal with today's episode is to begin extending these ideas to real substances using something called the principle of corresponding states. To remind you where we left off last time, here are the PV and PU diagrams for a 2D Lennard-Jones fluid measured using Dan Schroeder's web-based MD applet. As we discussed last time, these diagrams nicely illustrate the correlation between non-ideal behavior in gases and supercritical fluids and potential energy, manifest here as a negative deviation of internal energy, U, from the kinetic energy, expressed here as T. As long as the system remains single phase, we found we could model this behavior, at least qualitatively, using the Vander Waals equation of state. Comparing to the ideal gas law, this equation has an extra term expressing the expected reduction of pressure at surfaces due to attraction among the molecules. This term arises from the mean field approximation that negative potential energy will vary linearly with molecular density as the molecules get closer to each other. The equation also adjusts the free volume available for the molecules by subtracting a term proportional to the volume occupied by the molecules themselves. This term is negligible at large molar volumes, but becomes dominant as the molecules begin to crowd together. The Vander Waals equation is an example of what is known generally as an equation of state. There are many equations of state, including the ideal gas law itself, but they all have a common purpose, which is to describe how PV and T are related for a particular phase. As we saw with the Vander Waals equation, a second purpose is to express how potential energy in a system varies as a function of PV and T. As we'll see beginning next week, by combining this information with the first and second law analysis, we can also work out the relationships of PVT to internal energy and entropy. For now, though, let's just focus on PVT and potential energy and how these properties are related in real fluids. Before we go on, I'd like to briefly review the flow of logic leading us here. Last time I introduced you to the concept of attractive interactions among molecules, which are related to molecular properties like dipole moment, polarizability, ionization energy, or chemical interactions. I then introduced you to a model used to embody these interactions, the Lennard-Jones model, which has two parameters, epsilon, related to the energetic strength of the attraction, and sigma, related to the size of the molecules. We did some simulations, and then summarized the results using the Vander Waals equation, which invokes yet another set of parameters, A and B, A being associated with energetic strength of interactions, and B, which is related to the volume occupied by the molecules, and thus also their size. This is all fine from the standpoint of building our qualitative understanding. However, thinking back to all that discussion, at what point did I provide you with a quantitative relationship, bridging molecular properties to epsilon and sigma, or epsilon and sigma to macroscopic parameters A and B? This brings us to today's cartoon, a famous one by Charles Schulz, showing Lucy once again duping Charlie Brown with the promise of a field goal. If you're feeling like I've been playing a game of bait and switch with you, maybe it's because I have, but not because I wanted to. The problem is that for real fluids, predicting equation of state parameters from first principles is really hard and has only been done successfully in a few instances. So I'm not hiding these relationships from you. The problem is they just don't exist. This being the case, how do we obtain A and B, or other parameters that appear in our chosen equation of state? This brings us to today's topic. To begin, let's focus on the Vander Waals equation, which has only two parameters, A and B. As I showed you last time, it exhibits non-physical sigmoidal behavior below the critical point. Right at the critical point, it predicts that both the first and second derivative of pressure versus volume along the isotherm will go to 0. This is the only place on the PVT surface where this can happen. So one idea is to adjust A and B in the Vander Waals equation such that this behavior will occur at the critical point of a real fluid that we want to model. This results in a system of two equations and two unknowns that we can solve for A and B, with the results shown here. The critical pressure and temperature has been measured for most pure substances, and some of that data is summarized in Table A1 in our textbook. Thus, one approach to modeling a real fluid is to look up critical properties, calculate A and B, and then apply the Vander Waals equation. Note that other common equations of state, like Redlich-Kwong and Peng-Robinson, also use parameters usually labeled A and B. But since these are not molecular properties, they differ in value depending on which equation of state you're using. So be careful to look up the correct definition of A and B for the particular equation of state you're using. With the Vander Waals equation, if our problem involves known temperatures and volumes, we can always calculate pressure explicitly. However, often in chemical engineering, we have problems involving known temperatures and pressures, with volumes as an unknown. Rearranging the Vander Waals equation, we can see that it is cubic, meaning third order in volume, so hard to solve analytically for V. Other examples of cubic equations of state include Redlich-Kwong and Peng-Robinson. In these cases, we usually must solve for the volume indirectly using some kind of numerical approach. As an example, imagine we want to use the Vander Waals equation to model the molar volume of propane gas at high pressure. More specifically, let's calculate the volume at a pressure of 60 bar and a temperature of 135 degrees C. Let's also use the A parameter in the Vander Waals equation to calculate the molar potential energy. To do this, we'll get some help from Excel. I've posted the examples shown here on Canvas if you want to download and follow along. Whenever I do a spreadsheet calculation, I usually first build a data block that contains all the values of external constants and parameters that I'm going to need, as well as the units used to express these values. This is especially important since in a spreadsheet you can't carry units. So you really have to work the units out separately, for example using a sample calculation. Into the data block I've placed values of PC and TC for propane. R is expressed in liter bars per mole Kelvin since I want to work in volume units of liters per mole. I've also implemented the Vander Waals formulas for A and B based on the critical properties. Separately working out the units, they end up in units of liters per mole for B and liters square bar per mole squared for A. Moving to the right, after calculating the temperature in Kelvin, I generated a table for volumes so as to get a broad picture of the behavior along the 135 degrees C isotherm. In order to span a wide range with only a few values, I made a list of log V values spanning -1 to 2, which corresponds to 0.1 to 100 liters per mole. I then calculated the volumes at these points. In the third column here, I plugged in the Vander Waals equation for pressure and calculated it at 408 Kelvin over the range of volumes. Based on these values, we can see that for a pressure of 60 bar, we're going to have a volume around 0.25 or so liters per mole. One way to get a more precise answer is to make a plot and interpolate. This suggests a more precise value of maybe 0.26. To really nail it, though, we can set up a row with a volume that we iteratively adjust, either manually or using goal-seek. This gives a more precise answer of 0.27 liters per mole. Finally, in the last column, I've calculated the value of -A over V, which is the predicted potential energy according to the assumptions of the Vander Waals equation. This calculation includes a unit conversion from liter bars to kilojoules. Again, we could solve this graphically by using the volume we just determined to interpolate a plot of EP versus V. Alternatively, we can just copy the formula for potential energy down to the row where we iteratively calculated the volume previously. This gives a value of -3.6 kilojoules. Recall that all the predictions we made here using the Vander Waals equation were based on fitting A and B to a single data point of pressure and temperature at the critical point. That this works at all is truly remarkable and implies that all substances must behave rather similarly around their critical point. One way to take this idea one step further is to scale pressure and temperature to their values at the critical point, and then try to express volume, also scaled in some way, to scale pressure and temperature. This approach is known generally as the principle of corresponding states, used throughout chemical engineering for all kinds of properties, not just thermodynamic properties, but also transport properties like diffusivity, thermal conductivity, and viscosity. The way this is usually done is to define a reduced temperature and reduced pressure, which are temperature and pressure scaled to the critical properties. Molar volume is usually scaled to the value it would have assuming the gas were ideal, which is RT over P. This results in a dimensionless property called the compressibility factor, usually symbolized by the letter Z, defined as PV over RT. With this definition, Z goes to 1 when the gas is ideal. Under most circumstances involving strong attractive interactions, Z is less than 1, approaching 0 for liquids at low pressure. Z can also be greater than 1. This sometimes occurs at very high pressure when the molecules become crowded together. The name traditionally given to Z, the compressibility factor, is really a terrible name. The term compressibility sounds like it means the ease with which a substance can be compressed. That's what the isothermal compressibility kappa is. The quantity Z defined here has absolutely nothing to do with that. In fact, it's not a measure of compressibility at all. Z is really a property describing how much less volume or pressure a substance has relative to what it would have without molecular interactions. Recasting the Vander Waals equation in terms of P, R, T, R, and Z, we get the equation shown here with corresponding contour plot on the left for gases and supercritical fluids. The plot shows Z versus reduced pressure, with each line representing an isotherm at a particular reduced temperature. Note that at low pressure, Z, which is PV over RT, approaches 1, corresponding to ideal gas behavior. As the pressure is increased, Z becomes less than 1, indicating suppression of volume relative to ideal due to intermolecular attraction. Finally, at very high pressure, Z becomes greater than 1, indicating the inability of volume to decrease with pressure due to the crowding of the molecules. By definition, the critical point, marked in red, sits along the TR equals 1 isotherm, at a reduced pressure of 1. Here the Vander Waals equation predicts a value of Z equals 3/8, which is in the right ballpark for many substances, but usually not very accurate. Note that for TR less than 1, the lines just terminate. This occurs where the gas is expected to condense to a liquid, and thus have behavior that differs from the Vander Waals equation, making it meaningless to plot. If we sketch in the two-phase region on this diagram, it would look something like this, with the top of the saturation curve corresponding to gas and the bottom of the saturation curve corresponding to liquid. The tie lines in this case are vertical because the gas and liquid share the same pressure. This diagram is similar to a PV diagram, except it's flipped backward and rotated relative to the way we usually see it, with the gas on the right and the liquid on the left. Recall that according to the Vander Waals model, the potential energy is given by minus A over V. If we substitute in the expression for A in terms of the critical properties, and then scale the potential energy to R times the critical temperature, we obtain a quantity that reflects the relative importance of attractive interactions to kinetic energy. Rather than calling this a scaled potential energy, this quantity is usually called the internal energy departure function. The reason it has this name is because it represents the difference, or departure, of the internal energy from the value it would have as an ideal gas at the same temperature, where the molecules are too far apart to have any potential energy. A plot of this function is shown here. Just like the Lennard-Jones fluid, we see that when the pressure is low, the potential energy approaches 0, corresponding in the plot to Z approaching 1, in other words, an ideal gas. But as pressure is increased, and the molecules get closer to each other, they begin to interact with negative potential energy, and this causes a decrease in Z. Finally, as we saw with the Leonard-Jones fluid, the potential energy continues to decrease as the molecules get closer, even though there's an upward spike in Z due to molecular crowding. One nice thing about a set of plots like this is that they nicely map out the attractive interactions in a fluid at a given pressure and temperature, and the consequences of those interactions. Also, since the plots are explicit in pressure and temperature, they can be used to calculate volume directly. For example, consider the previous case of propane at 135 degrees C and 60 bar. Looking up the critical properties, we can directly calculate the reduced temperature, 1.1, and reduced pressure, 1.41, respectively. Consulting our diagrams, we see that at a reduced temperature of 1.1 and a reduced pressure of 1.41, we will have a value of Z equal to about 0.47 and an internal energy departure function of minus 1.15. Plugging these values into the definitions of Z and the departure function, we obtain a value of volume of 0.27 liters per mole and a value of potential energy of minus 3.5 kilojoules per mole. These are the same as we obtained by numerical simulation using our spreadsheet. The difference is that here we never calculated A and B, or even solved the Vander Waals equation. Instead, we used a pre-calculated solution based on scaled axes. This solution applies to any substance obeying the Vander Waals equation. All we had to do was calculate the reduced conditions and then re-express the scaled solution in dimensional form. One benefit of the corresponding states principle is that it can be applied to any equation of state model we want to, including more complex models that are hard to implement on a spreadsheet, as we did in the previous example. Calculation of the solution can be done once and summarized in charts and tables that can be used by anyone to calculate the properties of any substance. A prominent example provided in our textbook is the Lee-Kessler equation of state, which is quite accurate for a wide array of substances, but involves solving about a half a dozen simultaneous nonlinear algebraic equations. In fact, the author of our book does not provide details about the Lee-Kessler model or the equations involved. He just provides the solution and the tools to use it. As shown here, the form of the solution of the Lee-Kessler equation of state is similar to the charts I showed you for the Vander Waals equation. However, like Peng-Robinson and several other equations of state, Lee-Kessler adds an additional parameter, omega, called the eccentric factor, to improve accuracy. The solution is composed of two separate scaled functions of reduced temperature and pressure, a zeroth order function z0 and a smaller first order correction z1, which is multiplied by omega and added to z0. These functions are shown in tables 4.13 and 4.14 in the text and are also tabulated numerically in tables C1 and C2 in the appendix. The parameter omega is based on an insightful observation by Ken Pitzer that for spherical molecules like argon, the reduced saturation pressure just happens to fall exactly at 0.10 at a reduced temperature of 0.70. However, molecules with anisotropic interactions, such as chemical interactions, or molecules with long aspect ratios like high molecular weight alkanes, tend to have a lower reduced saturation pressure at the same reduced temperature. As defined here, omega is nearly zero for molecules obeying Pitzer's observation, while being significant for ones that don't. By adding omega as a parameter, the model can be made to better fit the data near the middle of the saturation dome. This parameter is called the eccentric factor due to its rough association with attractive interactions that are not spherically symmetric. Values for omega can usually be found tabulated with critical temperature and pressure. Based on the Lee-Kessler equation of state, one can also calculate the potential energy. Since workers often need to study open systems or systems at defined pressure, this potential energy is usually expressed as the departure of enthalpy from the enthalpy of an ideal gas at the same temperature and pressure. As with Z, this departure function is composed of two independent functions, a zeroth order term and a first order correction for molecules with non-zero eccentric factor. Focusing on the zeroth order term for a moment, you may notice the remarkable similarity to a pH diagram. To see this a bit more clearly, here is the same chart flipped backward and then compared to a pH diagram for H2O turned sideways. Drawing in the 500 degree C isotherm, which corresponds to a reduced temperature of about 1.2, we can see that the isotherms have identical shape. So really, these are the same plots, except in the Lee-Kessler chart, all the quantities have been scaled to the critical properties, and the intramolecular kinetic energy embedded in the ideal gas enthalpy has been removed. Examining the 500 degree C isotherm at low pressure, to the right side of the plot here, we see that under ideal gas conditions, the isotherm becomes parallel to the pressure axis, indicating that enthalpy becomes independent of pressure. This can be understood by considering what happens at the molecular level under these conditions, as pictured using the Lennard-Jones potential. When the molecules are far apart, as they are in an ideal gas, they have no potential energy, regardless of how far apart they become. Thus, changing the average distance between them by changing pressure and thus volume at constant temperature has no effect on potential energy. It stays close to zero. Under these conditions, the internal energy is only a function of temperature, since it only includes the temperature-dependent intramolecular kinetic energy possessed by individual molecules. Furthermore, since by definition enthalpy is internal energy plus PV, and PV equals RT for an ideal gas, the enthalpy is also only a function of temperature, not of pressure. U of T and H of T being independent of pressure or volume is really the hallmark of what makes an ideal gas an ideal gas. However, as pressure is increased and molecules become closer, they begin to interact, resulting in negative potential energy. This corresponds in the pH diagram to the enthalpy becoming less than it would be for an ideal gas, thus bending the isotherms to lower values of H, just as we saw for internal energy with the Vander Waals equation. Indeed, if we'd use the Lee-Kessler charts to calculate the enthalpy departure function, by substituting the definition of enthalpy, we can readily convert any value on the chart to an internal energy departure function in order to isolate the part of the enthalpy departure corresponding to potential energy. Returning to our working example of propane at 135 degrees C and 60 bar, let's see how accurate the Lee-Kessler equation of state is in predicting the volume and potential energy. From table A1, we can look up the value of the acentric factor for propane, 0.152, and add it to our list of properties. Reduced pressure and temperature are the same as we had before. Turning to the Lee-Kessler charts for Z0 and Z1, we can look along the TR equals 1.1 isotherm at PR equals 1.41 to find Z0, which is 0.5. Likewise, Z1 is around 0.15. Unfortunately, it's a bit hard to tell Z1 accurately from the graph, so in this case, it's probably a good idea to confirm this by going to the tabulated values for this function in the back of the textbook and checking. Sure enough, 0.15. Putting this together with the acentric factor, we get Z equals 0.52, somewhat higher than predicted by the Vander Waals equation. Plugging in dimensions again, we get a volume of 0.29 liters per mole, which is spot on the value found in the NIST database under these conditions. This means that the Vander Waals equation is about 7% off. Turning to the potential energy, we find that at TR equals 1.1 and PR equals 1.41, the zeroth order enthalpy departure function has a value of minus 1.95, and the first order correction is about minus 0.6. Checking the tabulated data again for better accuracy, it's more like minus 0.63. Factoring in the acentric factor again, we obtain a total enthalpy departure function of minus 2.05. Re-expressing this as an internal energy departure function using the formula I showed you earlier, we obtain a scaled potential energy of minus 1.52. Finally, redimensionalizing this by multiplying by RTC, we obtain a potential energy of minus 4.68 kilojoules per mole, a stronger interaction than predicted by the Vander Waals equation, and quite close to the value calculated from data in the NIST database for 60 bar versus 0 bar at 135 degrees C. What I hope these examples illustrate is that although it's hard to predict thermodynamic properties of real substances from molecular properties alone, the principle of corresponding states allows us to leverage our qualitative understanding of what's happening on the molecular level to make some amazingly accurate predictions extrapolated from just a few key data points. As we'll see next week, by combining equations of state with first law analysis, we can fully map out the relationship of internal energy of a real substance to other intensive properties, including an accounting of potential versus kinetic energy. What I hope these examples illustrate is that although it's hard to predict properties of real substances, the principle of corresponding states allows us to leverage our qualitative understanding of what's happening in the system to make some amazingly accurate predictions, extrapolating from just a few key data points. As we'll see next week, by combining equations of state with first law analysis, we can fully map out the relationship of internal energy of a substance to other intensive properties, including an accounting of potential versus kinetic energy.